Hi, I am Liu Fang, and I will be your instructor in this video detailing combined translational and rotational motion of an extended object. First, we will consider pure translational motion. The animation shows various points on a uniform solid sphere and how they move relative to a stationary observer on the horizontal surface. The center of the sphere is marked by the center of mass symbol. It is probable no surprise that all points on the sphere moves with the same velocity, including the center of mass. Let us call this the center of mass velocity. Next, we will consider pure rotational motion. In this case, the velocity of the center of mass is zero. For a solid object, all points aside from the center of mass must rotate at the same rotational rate for the object to maintain its shape. As the point is further away from the center, it must move a greater arc length in the same elapsed time, and its tangential speed must be greater as compared to points closer towards the center. The relationship between rotational and tangential speeds is the one we are already familiar with by relating arc length to the angle rotated through and the radius. The dashed line connecting the tip of two opposite velocity vector is suggestive of the linear relationship between the rotational and tangential speeds. This will become helpful later. Now we are ready to consider an object that rolls along a surface without slipping. This kind of motion is the superposition of the pure translational and pure rotational motions. The sphere to the right shows the translational and rotational velocity vectors that must be added, while the bottom illustration shows the result of the vector addition. We now see that it is a more complex picture than we may have expected. There are several important observations to be made. 1. The point in instantaneous contact with the ground is not moving at that given instant. This is a consequence of the no-slip condition. 2. Since the point of contact is not moving at that instant of contact, it is similar to the center of mass in the pure rotational case, and we can sketch a dashed line from that point to the tip of the top velocity vector. This is an important observation. The sphere is not rotating about its center, but instead it is rotating about the point of contact. To make this argument stronger, let us consider the following figure where we have drawn dashed lines from the point of contact to all the velocity vectors. We see that the dashed lines and velocity vectors are always perpendicular. This can only be true if the contact point is the center of rotation. Lastly, let us investigate the tangential speeds of the center of mass and the top point. For that purpose, let us bring in a new sketch. The dashed circle represents a sphere identical to our previous sphere, but centered at the point of contact or the center of rotation. Now it is clear that the center of mass is situated a distance equivalent to the radius away from the center of rotation, and the center of mass tangential speed is the rotational speed times the radius. Similarly, the top point is situated a distance of twice the radius, and its speed is double of the center of mass speed.